What if I told you that right now, as you rest here, entire galaxies are locked in an embrace that will take billions of years to complete? What if the most violent cosmic event imaginable unfolds so slowly that not a single star ever collides? This is galactic cannibalism, and it is perhaps the most beautiful, serene dance in all of existence. Tonight, you and I will drift through space and time to witness this ancient choreography. We will watch as gravity weaves galaxies together, as destruction becomes creation, and as the universe reveals one of its most profound secrets. Are you ready to see the cosmos in a way you never have before? Before we can understand how galaxies devour one another, we must first understand what a galaxy truly is. Imagine standing on a beach and looking out at an endless ocean. Each wave, each ripple is separate, yet all are part of the same vast body of water. Galaxies are like this. They are islands of hundreds of billions of stars, bound together by gravity, floating in the dark ocean of space. Our own Milky Way is just one such island, spinning slowly through the void. But unlike islands on Earth, these cosmic structures are not fixed in place. They move, they drift, and inevitably they encounter one another. What happens next is a story written across billions of years. You might think of space as empty, and in many ways it is. The distances between stars within a galaxy are so vast that if our sun were a grain of sand, the nearest star would be another grain of sand 4 miles away. But galaxies themselves are not scattered randomly. They cluster together in groups, in neighborhoods held together by invisible threads of gravity. These galactic communities ensure that over cosmic timescales, encounters are not just possible but inevitable. The universe has set the stage for a slow-motion ballet that has been choreographed by the fundamental forces of nature themselves. We are about to witness one such performance. Consider for a moment the age of the universe. 13.8 billion years have passed since the Big Bang. In that immense span of time, and many of them have met. Some encounters are brief, glancing blows that merely disturb the outer edges. Others are intimate, long embraces that reshape both participants completely. What we call galactic cannibalism is not truly an act of consumption in the way we understand it. No galaxy sets out to hunt another. There is no predator and prey. Instead, there is only gravity, patient and inexorable, drawing massive structures together across the cosmos. The term cannibalism might sound harsh, even violent, but I invite you to release those earthly associations. What we will explore together is not destruction but transformation. When galaxies merge, they do not obliterate each other. Instead, they create something new, something often more magnificent than either was alone. Think of it as two dancers becoming one performance, two rivers joining to form a greater waterway. The stars, the planets, the worlds that might harbor life all continue their journeys. They simply find themselves part of a new cosmic story written by gravity across billions of years. As we begin this journey together, I want you to adjust your sense of time. On Earth, we measure our lives in decades. Civilizations rise and fall in centuries or millennia. But galactic timescales are so vast that our human perspective becomes almost meaningless. A galactic merger unfolds over hundreds of millions, even billions of years. To watch galaxies collide is to watch the universe itself breathe in and out. It is a process so slow that if you could watch it in real time, you would see almost no movement at all. Yet it is happening right now in countless corners of the cosmos. Tonight, you and I are going to compress billions of years into a single hour. We will witness what no human could ever see with their own eyes. We will watch as galaxies approach each other across the void, as gravity begins its inexorable pull, as structures millions of light years across bend and deform. We will see stars ripped from their homes and sent streaming into the darkness. We will watch as galactic cores merge and supermassive black holes dance together. And through it all, we will discover something profound about the nature of change itself. Are you comfortable? Then let us begin our journey into the heart of galactic cannibalism. Our first destination is a pair of galaxies several 100 million light-years from Earth. From this distance, they appear as two perfect spirals, serene and separate. But appearances deceive. These galaxies are moving toward each other at hundreds of kilometers per second. That might sound fast, but given the immense distances involved, they have been approaching for hundreds of millions of years and will continue their dance for hundreds of millions more. By the time we are done, you will understand not just what is happening to these galaxies, but what will one day happen to our own Milky Way. The future of our cosmic home is already being written in the dance we are about to witness. Gravity is perhaps the most patient force in nature. Wait. It does not rush. It does not demand. It simply exists, creating wells in the fabric of space and time and inviting everything to fall toward those wells. Even now, as our two galaxies are still separated by millions of light years, gravity has already established a connection between them. Their gravitational fields overlap and intertwine like invisible hands reaching across the void. Can you imagine it? Two structures, each containing hundreds of billions of stars, beginning to feel each other's presence across distances so vast that light itself takes millions of years to cross them. This is the first whisper of their eventual embrace. What does it mean for galaxies to feel each other's gravity? After all, galaxies are not solid objects. They are vast clouds of stars, gas, and dark matter, held together only by their collective gravitational pull. When two such clouds begin to influence each other, the effects are subtle at first. The outermost stars in each galaxy might shift their orbits slightly, tugged by the combined gravitational field of both galaxies instead of just their own. These changes are imperceptible on human timescales. A star's orbit might shift by a fraction of a degree over 1,000,000 years. But add up millions of years, and those tiny tugs accumulate into something profound. As the galaxies continue their approach, something remarkable begins to happen. The gravitational interaction becomes stronger, and the galaxies start to deform. Imagine pulling on a piece of elastic fabric. At first, you see only the slightest give. But as you pull harder, the fabric begins to stretch noticeably. Galaxies behave in much the same way. Their outer edges begin to elongate, to reach toward their partner. Spiral arms that were once symmetrical start to become lopsided. The beautiful structure that took billions of years to form begins to change. But this is not damage. This is the beginning of something new. This is creation unfolding in slow motion. You and I are watching these galaxies from a vantage point outside of time, observing millions of years pass in moments. But if you were on a planet orbiting a star in one of these galaxies, you would notice almost nothing. The stars around you would continue their stately orbits. Your sun would rise and set as it always has. The night sky would look essentially unchanged from one generation to the next. Even over thousands of human lifetimes, the merger would be invisible. This is the paradox of galactic cannibalism. It is one of the most dramatic events in the universe, yet to anyone living through it, it unfolds so slowly as to be imperceptible. Time and scale transform violence into serenity. The gravitational dance intensifies as the distance between the galaxies continues to shrink. Now, instead of millions of light years apart, they are separated by hundreds of thousands. This is still an unimaginable distance by human standards, but in cosmic terms, they are neighbors now, close enough that their interaction dominates both of their evolutions. The dark matter halos that surround each galaxy, invisible but immensely massive, begin to merge first. These halos extend far beyond the visible stars, and their collision creates ripples in the gravitational field that influence everything within them. The stage is set for the visible spectacle to come. Within each galaxy, something subtle but important is beginning to happen. The gravitational perturbations are triggering small pockets of star formation. When gas clouds are jostled by gravitational waves, they can collapse and ignite into new stars. Even this, early in the merger, the process is already creating new light. New stars are being born because of this encounter. It is a preview of what is to come. In the later stages of the merger, star formation will explode into a frenzy unlike anything the galaxies experienced in isolation. But for now, it is just a whisper, a hint of the creative power that gravity wields when it brings galaxies together. Let us pause here for a moment and consider what we are truly witnessing. These are not random events. They are not cosmic accidents. Gravity is a fundamental property of mass and energy woven into the very structure of space-time. When galaxies form, merge, and evolve, they are following paths determined by the laws of physics laid down at the beginning of the universe. There is something profoundly beautiful in that. The dance we are watching is as inevitable as it is magnificent. It was always going to happen. From the moment these galaxies formed, their futures were intertwined. We are simply privileged enough to watch it unfold. The distance has now closed to tens of thousands of light years. For the first time, the galaxies are near enough that tidal forces begin to dominate the interaction. What are tidal forces? You experience them on Earth in a gentle way when the moon's gravity pulls on our oceans, creating tides. But imagine that force scaled up billions of times, acting on structures made of hundreds of billions of stars. Tidal forces arise because gravity weakens with distance. The side of each galaxy facing its partner feels a stronger pull than the far side. This difference in gravitational strength across the galaxy's body begins to stretch it, to tear at its structure in a way that is both violent and exquisitely beautiful. As tidal forces intensify, the first true casualties of the merger begin to appear. Stars on the outer edges of both galaxies, stars that orbit far from their galactic cores, find themselves caught between two gravitational masters. Some are pulled away entirely, ejected from their home galaxy and sent streaming into the space between the two colliding systems. These are called tidal tails, and they are among the most beautiful structures in astronomy. Long, graceful arcs of stars extending hundreds of thousands of light years into space, shimmering like cosmic rivers. Each point of light in these tails is a sun, perhaps with planets, perhaps with life, now adrift in intergalactic space. Let your mind wander for a moment to a hypothetical planet orbiting a star in one of these tidal tails. What would the night sky look like from such a world? Behind you, you would see your home galaxy, now distorted and strange, its structure clearly warped by the ongoing merger. Ahead of you, the approaching galaxy would dominate the sky, its spiral arms and bright core filling your view with light. And all around you, scattered through the darkness, would be the other exiled stars, your fellow travelers on this cosmic journey into the unknown. It would be a sky like no other, a reminder that you are witnessing one of the universe's grandest transformations from the inside. The beauty of tidal tails is not merely aesthetic. They tell us profound truths about the nature of galaxies and the role of dark matter. You see, if galaxies were made only of visible stars and gas, tidal tails would look different than they do. The fact that tails form the way they do, with particular shapes and distributions, reveals the presence of dark matter halos. These invisible structures shape the visible matter's behavior. By studying tidal streams in merging galaxies, astronomers have confirmed that dark matter exists and mapped its distribution. What appears as simple beauty is also a cosmic revelation, nature offering up secrets in the most elegant way possible. As we watch, the two galaxies make their first close passage. This is a critical moment. They sweep past each other, their edges almost touching, their gravitational fields locked in an intense interaction. The tidal forces reach their peak, and material is ripped from both systems in great luminous streamers. But here is something remarkable to consider. Despite this apparent violence, despite the fact that billions of stars are being redistributed across space, the actual chance of any two stars colliding is essentially zero. The distances between stars are so vast that they pass through each other's galactic disks like ghosts, unaffected except by gravity's invisible hand. After their first close encounter, the galaxies do not immediately merge. Instead, they continue past each other, their mutual gravity having slowed but not stopped their relative motion. They begin to separate again, moving apart into space. But the dance is not over. Far from it. The gravitational interaction has robbed them of energy and angular momentum. They are now bound to each other, doomed to fall back together again. Over the next few 100 million years, they will swing apart, slow, stop, and begin falling back toward each other for a second passage. Good. And then a third. Each passage will be more intimate than the last, until finally they can no longer separate at all. There is something almost tender about this repeated approach and retreat. Like partners in a dance learning each other's rhythms, the galaxies are caught in a gravitational embrace that will only tighten with time. Each passage strips away more material, creating more tidal features, warping the structures further. With each orbit, they lose energy to gravitational interactions, and the distances between passages shrink. What began as a gentle gravitational whisper across millions of light years has become an intimate dance that will ultimately result in a complete merger. We are watching inevitability unfold, written in the trajectories of hundreds of billions of stars. Let us now turn our attention more closely to the tidal streams themselves. These structures are among the most delicate and beautiful features created by galactic interactions. They are visible evidence of gravity's ability to sculpt matter on the largest scales imaginable. Each stream is a river of stars, stretching across hundreds of thousands of light years, yet often only a few thousand light years wide. Within these streams, stars travel together, following nearly identical orbits, refugees from their parent galaxies bound together by shared circumstance. If you could measure the velocities of stars within a tidal stream, you would find them moving in eerie synchrony, like a school of fish flowing through cosmic ocean currents. The formation of these streams is a consequence of precise physics. As tidal forces pull stars away from their galaxy, those stars do not scatter randomly. Instead, they follow specific trajectories determined by their initial positions and velocities, and by the gravitational potential of both galaxies. Stars stripped from the near side of a galaxy form one stream, flowing ahead of the galaxy in its orbit. Stars stripped from the far side form another stream, trailing behind. Over time, these streams can wrap around the merging system multiple times, creating complex, looping structures that trace out the history of the gravitational interaction in exquisite detail. Astronomers treasure tidal streams because they are archaeological records of galactic cannibalism. By studying the positions, velocities, and chemical compositions of stars in a stream, we can reconstruct when and how the interaction occurred. we can determine the mass of the galaxies involved, the angle of their collision, even details about the dark matter distributions. In our own Milky Way, we have discovered numerous tidal streams, remnants of smaller galaxies that our galaxy has consumed over billions of years. Each stream is like a fossil, preserving information about cosmic events that happened long before Earth existed. They are messages from the deep past, written in starlight and decoded by patient observation. There is something poignant about tidal streams when you consider what they represent on an individual scale. Each star in a stream once belonged to a galaxy, nested within that galaxy's structure and gravitational well. Those stars may have orbited their galactic center for billions of years, stable and content in their cosmic home. Then, through no action of their own, they were torn away and sent drifting through intergalactic space. Yet they persist. They continue to shine. If they have planets, those worlds continue to orbit. Life, if it exists there, would continue. The exile does not extinguish them. It merely changes their story, making them part of a larger narrative of cosmic transformation. Not all tidal streams are created equal. Some are coherent and narrow, maintaining their structure for billions of years. Others quickly disperse, their stars spreading out until the stream becomes indistinguishable from the general stellar population. The longevity of a stream depends on many factors, including the masses of the galaxies involved, the trajectory of the interaction, and the presence of other gravitational perturbations. In dense galactic environments, tidal streams are constantly being disturbed by nearby galaxies, causing them to blur and fade. In isolation, they can persist as distinct structures for extraordinary lengths of time, cosmic monuments to interactions that occurred eons ago. As we watch our merging galaxy pair continue their dance, their tidal streams grow longer and more complex. With each passage, more material is stripped away. Some of this material will eventually fall back into the merging system, raining down onto the newly forming galaxy at the center. Other streams will escape entirely, becoming part of the intergalactic medium, orphaned stars wandering forever between galaxies. This redistribution of material is an important process in cosmic evolution. It enriches the space between galaxies with heavy elements forged in stars, elements that may one day be incorporated into new galaxies or star systems. Nothing is truly lost, only transformed and redistributed across space and time. Before we move on to the next phase of our cosmic story, take a moment to appreciate the sheer scale and beauty of what we have explored. Tidal streams, these delicate ribbons of starlight stretching across the void, are monuments to the power of gravity and the resilience of structure in the universe. They remind us that even in events we label as violent or destructive, there is profound order and beauty. The universe does not create chaos. It creates pattern, structure, and new forms of organization. What appears to be an ending is always, in some sense, a beginning. The streams we have explored are not scars of destruction. They are brushstrokes in an ongoing cosmic masterpiece. We return now to the broader dance of our two galaxies. After their first close passage, they have swung apart to a distance of hundreds of thousands of light years. But their separation is temporary, a breath between movements in a long performance. The gravitational bond between them ensures they will fall back together. Over the next 200 million years, they slow, stop, and begin their second approach. This passage will be even more intimate than the first. More tidal features will form. More stars will be redistributed. The structures of both galaxies will become increasingly unrecognizable, their original spiral forms warping into chaotic, asymmetric shapes that defy simple description. With each passage, the galaxies lose orbital energy and angular momentum. Where does this energy go? It is transferred to the stars themselves. Stars in the outer regions gain energy and are flung outward, some escaping entirely. Stars in the inner regions lose energy and sink toward the center. This process, called dynamical friction, is the mechanism that causes the orbital decay. The collective gravitational influence of billions of stars acts like a drag force on the galaxy's orbital motion, slowly but inevitably drawing them closer together. It is a perfect example of how the collective behavior of vast numbers of objects can create emergent effects that change the system as a whole. By the third close passage, the galaxies no longer resemble their original forms. The beautiful spiral structures that took billions of years to develop have been scrambled. Arms are broken, cores are distorted, and tidal features dominate the appearance. To an external observer, it might look like cosmic carnage. But remember our shifted perspective. From within the galaxies, life continues undisturbed. Stars continue their orbits, now in more chaotic paths, but still safely separated from one another. Planets orbit their suns. The day-to-day existence of hypothetical civilizations proceeds normally. The merger is apocalyptic on galactic scales, but routine on smaller scales. It is all a matter of perspective. It is worth pausing to consider what happens to the gas during these repeated passages. Unlike stars, which are point sources that almost never collide, gas clouds can and do collide. When giant molecular clouds from two galaxies interpenetrate, they shock and compress each other. This compression triggers intense star formation. During the multiple passage phase of a merger, we see bursts of star formation spread throughout both galaxies. New stars, young, hot, and bright, illuminate the gas clouds from within, creating spectacular stellar nurseries visible across intergalactic distances. The merger is not just redistributing existing stars. It is catalyzing the birth of new ones. The timeline of a major galaxy merger can span 1 billion years or more from first approach to final coalescence. During this time, the universe itself does not stand still. Other galaxies continue their journeys through space. New stars are born, and old stars die in countless systems across the cosmos. Supernovae explode. Black holes grow. The cosmic web continues its slow, patient restructuring of matter. Our merging galaxies are participating in this grand cosmic evolution, their transformation part of a much larger story that encompasses the entire universe. They are both actors on the stage and part of the stage itself, simultaneously influencing and being influenced by the cosmic environment around them. By the fourth or fifth passage, the distinction between the two galaxies begins to blur completely. Their stellar populations have mixed to such a degree that it becomes difficult to say which stars belong to which original galaxy. The tidal tails and streams, once distinctly associated with one parent or the other, have become a general halo of debris surrounding the merger. At the center, a single, massive structure is beginning to form. This is the proto-remnant, the nascent galaxy that will emerge from this union. It bears little resemblance to either parent. It is something new, forged in the gravitational crucible of the merger, a creation that could not have existed without this encounter. As we watch the orbital separation decrease with each passage, we can sense the approaching conclusion of this phase. The galaxies are now so close and so distorted that they are on the verge of final coalescence. The gravitational binding energy has been radiated away through dynamical interactions. The angular momentum has been redistributed outward to the stars in the tidal tails. What remains at the center is a bound system that will never separate again. The dance is nearly complete. The waltz that began hundreds of millions of years ago across vast gulfs of space is about to conclude with an intimate, final merger. We are approaching the climax of galactic cannibalism, the moment when two become one. We now arrive at one of the most remarkable phases of galactic cannibalism. The galactic cores, each containing supermassive black holes millions to billions of times the mass of our Sun, are spiraling toward each other. This is no longer a dance of entire galaxies, but of their gravitational hearts. The physics at play here is extreme. The gravitational potentials are immense. Space-time itself is warped and twisted by the presence of so much mass in such a relatively small volume. If we could see gravity, we would witness space-time forming deep wells around each black hole, wells that are now merging into a single, profound distortion in the fabric of the universe. As the two supermassive black holes orbit each other, they begin to emit gravitational waves. These are ripples in space-time itself, carrying energy away from the system. Gravitational waves are one of the most profound predictions of Einstein's general relativity, and for decades they were purely theoretical. But in recent years, we have detected them directly, confirming that massive objects in motion do indeed create waves that propagate through the cosmos at the speed of light. In a galaxy merger, the gravitational waves from enspiraling black holes carry away orbital energy, causing the black holes to spiral closer together ever faster. It is a runaway process leading to an inevitable conclusion. Surrounding each supermassive black hole is an accretion disk, a swirling maelstrom of gas and dust spiraling inward toward the event horizon. These disks glow with intense radiation as friction heats the unfalling material to millions of degrees. When two such systems come together, their accretion disks interact in complex and spectacular ways. Gas streams from one disk to the other. Shock waves propagate through the material. Jets of high-energy particles are launched from the poles of the black holes, beaming radiation across the cosmos. The merger becomes not just a gravitational event, but one of the most energetic electromagnetic phenomena in the universe, visible to observers halfway across the cosmos. Let us zoom out slightly and consider what is happening to the stars in the galactic cores during this time. Near the center of the merger, stellar densities are extraordinarily high compared to the galactic outskirts. Thousands of stars may exist within a single cubic light year. Even so, direct collisions remain rare. What does happen is gravitational scattering. Stars pass close enough to the merging black holes to have their orbits dramatically altered. Some are accelerated to tremendous speeds and ejected from the galaxy entirely, becoming hypervelocity stars traveling through intergalactic space at thousands of kilometers per second. Others lose energy and sink even deeper into the gravitational well, joining the dense stellar cusp that forms around the merged black hole. The final approach of the two black holes is swift by cosmic standards. Once they are within a few light years of each other, the emission of gravitational waves accelerates their inspiral dramatically. Over perhaps 1,000,000 years, which is an eye blink in galactic time, they spiral from light years apart to light minutes apart to, finally, contact. In the final seconds before merger, they orbit each other hundreds of times per second, emitting gravitational waves of extraordinary power. The amount of energy radiated in those final moments exceeds the combined light output of all the stars in the observable universe. It is one of the most powerful events possible in nature, second only to the Big Bang itself in the amount of energy released in such a short time. And then, in a moment that marks the true completion of galactic cannibalism, the two black holes merge into one. Their event horizons touch and combine, forming a single, larger black hole. In this instant, several solar masses worth of energy is radiated away as gravitational waves, causing the newly merged black hole to ring like a bell struck with cosmic force. The frequency and decay of this ringing tell us about the mass and spin of the final black hole. Astronomers call this the ring-down phase, and it is one of the most distinctive signatures of a black hole merger. It is also the final chord in the gravitational symphony that has been playing since the galaxies first felt each other's pull across the void. The merged supermassive black hole does not remain quiet for long. It quickly begins accreting material from its surroundings, material that was stirred up and funneled inward by the merger process. The resulting active galactic nucleus, or AGN, becomes one of the brightest objects in the universe, outshining the combined light of all the stars in its host galaxy. These quasar phases, as they are called, are among the most luminous phenomena known. They can be detected across billions of light years, beacons of galactic cannibalism visible across most of the observable universe. What we see as extreme violence and energy is also, in a sense, an announcement. It is the universe declaring that something new has been created here, something worth noticing across cosmic distances. We have reached a philosophical turning point in our journey. We have witnessed immense changes, the dismantling of galactic structures that took billions of years to form, the ejection of stars from their homes, the collision of supermassive black holes. By earthly standards, we would call this destruction. But is it? Wait. The stars still exist. The gas still exists. The matter and energy have been redistributed, not destroyed. What we have really witnessed is transformation on the grandest scale imaginable. This is the paradox of galactic cannibalism. It is creation through apparent destruction. It is the universe's way of building new structures from old ones, of evolving complexity through merger and interaction. Consider for a moment the burst of star formation triggered by the merger. When the gas clouds from two galaxies collide, they compress each other, creating regions of extreme density where new stars can form. In the most intense merger-driven starbursts, stars form at rates hundreds of times faster than in quiescent galaxies like the Milky Way. Millions of new stars are born in the span of just a few tens of millions of years. These stars would never have existed without the merger. The interaction did not destroy potential, it realized it. It took diffuse gas that might have taken billions more years to form stars and accelerated the process dramatically. This is creation, not destruction. The young stars born in merger-driven starbursts are massive and short-lived. Many will explode as supernovae within just a few million years of their birth. These supernovae enrich the surrounding gas with heavy elements, elements forged in the nuclear furnaces of stellar cores. Carbon, oxygen, nitrogen, iron, and dozens of other elements are blasted into the interstellar medium, where they will eventually be incorporated into the next generation of stars and planets. Every atom of your body heavier than hydrogen was created in a star and dispersed by processes like this. The mergers that seem so violent are also the cosmic forges that created the building blocks of life itself. They are not destructive. They are generative. Let us also consider the fate of planetary systems during mergers. It is true that some planets will be ejected when their host stars are flung from the galaxy, but the vast majority survive. They continue to orbit their suns as they always have, now simply in a different galactic context. In fact, some astrobiologists have suggested that mergers might even promote the spread of life. When stars are scattered to new regions of their galaxy, they carry their planets with them. If life exists on those planets, it is essentially being disseminated to new environments. The merger becomes a mechanism for mixing the galactic gene pool, if you will, spreading the seeds of life to regions where it might otherwise never reach. There is beauty, too, in the morphological transformation that mergers cause. Spiral galaxies with their elegant arms and ordered rotation are transformed into elliptical galaxies, which are rounder, smoother, and more chaotic in their stellar motions. To some, elliptical galaxies might seem less interesting, lacking the intricate structure of spirals. But they have their own beauty. Their smooth light distributions, their three-dimensional shapes ranging from spheres to elongated ellipsoids, their ancient stellar populations glowing with warm reddish light. They are monuments to past interactions, galaxies that have lived through cosmic upheaval and emerged transformed. They are, in a sense, the wise elders of the galactic zoo, carrying within them the history of everything they have experienced. The remnant galaxy that forms from our merger will be massive, potentially more massive than either parent galaxy was alone. It will contain all the stars from both original galaxies, plus millions of new stars born during the interaction. It will have a large central bulge housing the merged supermassive black hole. Around this core will be an extended halo of stars, many in chaotic, highly elliptical orbits. Globular clusters, ancient collections of stars that survived the merger intact, will orbit in the outer reaches. And scattered throughout intergalactic space will be the tidal streams and orphan stars, permanent reminders of the interaction that created this new cosmic structure. Every feature tells part of the story. As we contemplate this transformation, I want you to consider what it means to witness change on such a scale. On Earth, we often resist change. We cling to familiar structures and mourn their passing. But the universe teaches a different lesson. Everything changes. Or stars are born and die. Galaxies merge and transform. Even the universe itself is expanding and evolving. But change is not loss. It is transformation. The atoms that made up the original galaxy still exist. They have simply been rearranged into new patterns, new structures. The information and complexity have not decreased. They have increased. This is not an end. It is a new beginning, written in starlight across billions of light years of space. Let us now dive deeper into one of the most creative aspects of galactic mergers, the ignition of massive star formation. We have touched on this already, but it deserves closer attention because it represents the most direct way that mergers create rather than destroy. When two galaxies collide, their interstellar gas clouds, which are normally stable and slow to form stars, are suddenly compressed. This compression increases the density and pressure in the clouds, triggering gravitational collapse. Regions that might have remained stable for billions of years suddenly become unstable, collapsing into new stars within mere millions of years. The merger acts like a cosmic midwife, bringing starbirth forward in time. The star formation in merger-driven starbursts is not evenly distributed. It concentrates in specific regions where the gas clouds have collided most directly. These are often in the tidal bridges between the galaxies or in the chaotic central regions where material from both galaxies is mixing. If you could observe such a galaxy in different wavelengths of light, you would see that these starburst regions glow brilliantly in ultraviolet light from hot young stars, in visible light as those stars illuminate surrounding nebulae, and in infrared light as dust heated by starlight radiates its energy. They are cosmic beacons, announcing centers of creation where the universe is actively making new stars at an extraordinary rate. One of the most famous examples of merger-driven star formation is found in the antennae galaxies, two spiral galaxies caught in the act of merging about 60 million light-years from Earth. When observed with powerful telescopes, the antennae reveal hundreds of superstar clusters, each containing millions of young stars packed into regions just tens of light-years across. These clusters are so bright that each one outshines our entire Milky Way galaxy in certain wavelengths. They represent star formation on steroids, driven by the compression and shocking of gas during the merger. Studying the antennae and similar systems gives us a preview of what our own galaxy might experience when it merges with Andromeda billions of years from now. The massive stars born in these starbursts live fast and die young. Stars with masses 10, 50, even 100 times that of our Sun burn through their nuclear fuel in just a few million years. When they die, they do so spectacularly as supernovae or hypernovae, explosions so bright they can briefly outshine their entire host galaxy. These explosions inject enormous amounts of energy back into the surrounding gas, creating shock waves that can actually shut off star formation by heating and dispersing the remaining gas clouds. Thus, starburst episodes are self-limiting. They ignite with incredible intensity but burn out relatively quickly, leaving behind populations of young stars and enriched gas ready for the next generation. Not all star formation emerges is in spectacular starbursts. There is also a longer-term, more sustained increase in star formation as gas is funneled toward the center of the merging system. The gravitational torques created by the asymmetric distribution of mass during a merger can drive gas inward, increasing the density in the central regions and creating an extended period of elevated star formation. This process can continue for hundreds of millions of years, long after the initial starburst has faded. It represents a more gentle but no less significant contribution to the creation of new stars, a slow but steady transformation of diffuse gas into stellar populations. There is also the question of what happens to the dust during these interactions. Interstellar dust, composed of tiny grains of silicates and carbon compounds, plays a crucial role in star formation by cooling the gas and providing surfaces where molecules can form. During mergers, some dust is destroyed in the high-energy environments of starbursts and supernovae. But new dust is also created, forged in the atmospheres of dying stars and in supernova ejecta. The dust content of a galaxy can actually increase during a merger as massive stars progress rapidly through their life cycles and release new dust into space. This dust will go on to play a role in forming the next generation of stars and planets in the merger remnant. As we conclude this exploration of star formation and mergers, reflect on the creative power we have witnessed. Gas that might have remained inert for eons is activated. Stars that might never have formed come into being. Entire stellar clusters, massive gravitationally bound groups of stars, are created in events that unfold on timescales short by cosmic standards. The merger has taken potential and realized it turned possibility into actuality. And with each new star comes the potential for planets, for chemistry, perhaps even for life. Galactic cannibalism is not an end to stories. It is the beginning of countless new ones, each star a new possibility, each stellar system a new chapter in the ongoing narrative of the cosmos. Billions of years have passed since our two galaxies first began their approach. The dance is nearly complete. What remains is a single, massive structure, an elliptical galaxy formed from the merger of two spirals. This is the typical outcome of major mergers between galaxies of comparable mass. The beautiful spiral structures, with their organized rotation and distinct arms, have been destroyed. In their place is a galaxy with a more chaotic internal structure, where stars move in all directions on a variety of orbits. But this chaos has its own order, its own beauty. Let us explore this new creation and understand what makes elliptical galaxies unique and important in cosmic evolution. The most immediately obvious difference between elliptical and spiral galaxies is their shape. Spirals are flat disks with most of their stars orbiting in the same plane. Ellipticals are three-dimensional structures, roughly spheroidal or ellipsoidal in shape. Their stars orbit in all directions with no preferred plane. This is a direct consequence of the merger process. The violent gravitational interactions during the merger scrambled the orderly orbits of the spiral galaxies, pumping energy into random motions and puffing up the structure into 3 dimensions. What might seem like a loss of order is actually the system finding a new equilibrium, one that reflects the complex history of interactions that created it. Elliptical galaxies contain very little gas and dust compared to spirals. Most of their interstellar medium was either consumed in the starburst during the merger, ejected by supernovae and stellar winds, or locked up in stars. With little gas remaining, elliptical galaxies have very low rates of ongoing star formation. The stars we see in an elliptical are predominantly old, formed long ago, either before the merger or during it. These old stars give ellipticals their characteristic reddish or yellowish color, in contrast to the blue tints of spiral galaxies where young stars continuously form. An elliptical galaxy is, in a sense, retired, its active star-forming days behind it, now simply aging gracefully through cosmic time. Despite their lack of ongoing star formation, elliptical galaxies are far from boring. They are the most massive galaxies in the universe. Giant ellipticals found at the centers of galaxy clusters can contain trillions of stars, 10 or more times the mass of the Milky Way. Their supermassive black holes are proportionally larger as well, some reaching billions of times the mass of the Sun. These black holes, fed by gas funneled inward during mergers, often remain active as quasars or radiogalaxies, shooting jets of particles thousands of light years into space. The most massive ellipticals are cosmic giants, dominating their environments and shaping the evolution of entire galaxy clusters through their gravity and energy output. Elliptical galaxies also host impressive systems of globular clusters. These ancient, tightly bound groups of stars orbit in the halos of ellipticals by the thousands. Each globular cluster can contain hundreds of thousands to millions of stars packed into a sphere just dozens of light years across. Some of these globular clusters are relics from the progenitor spiral galaxies, survivors of the merger that maintained their integrity through the chaos. Others may have formed during the merger itself, born in regions of intense star formation and somehow managing to remain bound despite the turmoil. They orbit the elliptical like a swarm of luminous bees around a massive hive. One might ask whether elliptical galaxies can ever return to being spirals. The answer is generally no. Once the gas is gone and the stellar orbits are randomized, there is no mechanism to reassemble a disk structure. However, ellipticals can and do continue to grow through further mergers. When an elliptical merges with another galaxy, whether spiral or elliptical, it simply incorporates that galaxy's stars and mass, becoming larger but maintaining its elliptical morphology. In the densest regions of the universe, like the cores of galaxy clusters, the largest ellipticals grow through the gradual cannibalization of smaller neighbors, a process that can continue throughout the entire lifetime of the universe. They are cosmic accumulators, forever growing through merger and acquisition. As we observe our newly formed elliptical galaxy settling into its new equilibrium, we can appreciate the transformation we have witnessed. Two spiral galaxies, each beautiful in their own right, have become something different but no less magnificent. The elliptical galaxy is a monument to cosmic history, its structure encoding information about every interaction it has experienced. Its stars carry chemical fingerprints from the starbursts that occurred during the merger. Its tidal streams, now fading but still traceable, map out the gravitational choreography of the collision. Everything about it tells a story, and that story is written in a language of light and gravity for anyone with the knowledge to read it. This is not an end, but a transformation, one chapter closing and another beginning. We have followed the story of galactic cannibalism from first approach to final merger, from two distinct spirals to a single massive elliptical. But our story does not end here. We must zoom out once more, not just in space but in time, and consider the role that mergers play in the long-term evolution of the universe. Galactic cannibalism is not an isolated event, but a fundamental process that has shaped cosmic structure throughout the history of the universe. Every large galaxy has experienced mergers. Every elliptical galaxy is the product of at least one major merger, and usually many. The universe has been recycling and reshaping its galactic structures for over 13 billion years. In the early universe, just a few 100 million years after the Big Bang, galaxies were smaller and more irregular than they are today. These primordial galaxies were the first structures to emerge from the nearly uniform sea of matter left over from the Big Bang. But they did not remain separate. Almost immediately, they began to interact and merge, building up larger structures through a process astronomers call hierarchical assembly. Small galaxies merge to form medium galaxies. Medium galaxies merge to form large ones. And this process has continued with decreasing frequency but ongoing, still, throughout cosmic history. The grand spiral and elliptical galaxies we see today are the accumulated result of billions of years of mergers. Mergers are less common today than they were in the early universe, but they still occur. In dense environments like galaxy clusters, where hundreds or thousands of galaxies are packed into a relatively small volume of space, mergers and interactions are ongoing. In more isolated regions like the local group that contains the Milky Way, major mergers are rarer but still inevitable on long enough timescales. The universe is still evolving, still reshaping itself, though at a slower pace than in its youth. If we could watch the cosmos for trillions of years, we would see mergers continuing, galaxies growing larger and more massive as time progresses, until eventually the expansion of the universe spreads, remaining galaxies too far apart for further interactions. One of the most important insights from studying galactic cannibalism is the realization that galaxies are not permanent, unchanging structures. They have life cycles. They grow through accretion and merger. They transform morphologically when they collide. They exhaust their gas supplies and stop forming stars. They may be rejuvenated by fresh infalls of gas. They can be destroyed by tidal forces or incorporated into larger systems. In every sense, galaxies are alive, not biologically but evolutionarily. They are born, they grow, they interact, they age, and they transform. Understanding this dynamic nature of galaxies has revolutionized our view of cosmic structure and the processes that shape it. Mergers also play a crucial role in the growth of supermassive black holes. These enigmatic objects, millions to billions of times the mass of the Sun, lurk at the centers of most large galaxies. How did they grow so massive? Part of the answer is mergers. When galaxies merge, their central black holes merge, creating a larger black hole. Additionally, the gas funneled inward during mergers provides fuel for black hole growth. The merger-driven starburst and AGN activity we discussed earlier both contribute to black hole feeding. Over cosmic time, through repeated mergers, black holes have grown from relatively modest seeds into the supermassive behemoths we observe today. The evolution of galaxies and the evolution of their central black holes are intimately connected, two aspects of the same cosmic story. Let us also consider the role of dark matter in this cosmic recycling. Dark matter halos surround all galaxies, extending far beyond the visible stars. When galaxies merge, their dark matter halos merge as well, creating larger combined halos. In fact, the dark matter merges first, before the visible matter, setting the gravitational stage for the baryonic matter to follow. The structures we see in the visible universe, the galaxies and galaxy clusters, are really just the luminous tips of much larger dark matter structures. Understanding mergers requires understanding dark matter, and vice versa. The invisible and visible are intertwined in the cosmic dance, each influencing the other in ways we are still working to fully understand. From the perspective of cosmic recycling, galactic cannibalism is ultimately conservative. Matter and energy are not created or destroyed in these events, only rearranged. The same atoms that made up the original galaxies make up the merger remnant. But the arrangement matters. Structure matters. Organization matters. By transforming spirals into ellipticals, by triggering starbursts that forge new elements, by redistributing matter across vast distances, mergers increase the complexity and diversity of the universe. They take simple structures and create intricate ones. They take homogeneity and create heterogeneity. In doing so, They drive cosmic evolution forward, ensuring that the universe becomes ever more complex and interesting as time progresses. This is the deep beauty of galactic cannibalism. Throughout this journey, we have explored galactic cannibalism as something happening to distant galaxies, structures hundreds of millions or billions of light years away. But now, let us bring the story home. Our own Milky Way galaxy is not immune to this cosmic process. In fact, we are currently on a collision course with our nearest large neighbor, the Andromeda galaxy. In approximately 4 billion years, these two galaxies will begin their gravitational dance, and everything we have discussed tonight will unfold in our own cosmic backyard. This is not speculation. This is prediction based on precise measurements of Andromeda's motion through space. Our future is written in the gravitational pull between two islands of stars. Andromeda is slightly larger than the Milky Way, containing perhaps 1 trillion stars compared to our galaxy's few 100 billion. But in galactic terms, we are comparable in size. This will be a merger of near equals, much like the one we have been following throughout this journey. When Andromeda and the Milky Way collide, they will create one of the most spectacular merger events in the local universe. From an external vantage point, an observer would see two magnificent spirals approaching each other, developing tidal tails, experiencing starburst episodes, and ultimately merging into a giant elliptical galaxy. From inside the event, from Earth, if it still exists, the view will be even more extraordinary. What will the sky look like from Earth as the merger unfolds? Currently, Andromeda appears as a faint smudge in our night sky, barely visible to the naked eye. As the galaxies approach, Andromeda will grow larger and brighter, eventually dominating the night sky. Billions of years from now, instead of a small fuzzy patch, our descendants will see a massive spiral galaxy stretching across the heavens, its spiral arms resolved into individual stars and clusters, its core a brilliant jewel of light. The sight will be beyond anything humanity has ever witnessed, a cosmic spectacle visible to the naked eye that transforms the appearance of the night itself. It will be beautiful beyond description. Should we fear this event? Not at all. Remember that even in a galactic collision, stars almost never collide. Our Sun and solar system will be swept up in the merger, our orbits altered, perhaps moved to a different region of the resulting elliptical galaxy. But Earth itself will not be harmed by the merger process. The much greater concern for Earth's distant future is the evolution of the Sun itself. In about 1 billion years, the Sun will begin to heat up as it ages, eventually rendering Earth uninhabitable. The galactic merger, occurring 4 billion years from now, happens long after Earth would have already faced its own solar system crisis. The galaxy may be colliding, but Earth's fate is tied to its star, not its galaxy. The merger of the Milky Way and Andromeda will likely trigger bursts of star formation as gas clouds collide. New stars will be born, including massive, brilliant ones that will light up stellar nurseries throughout the merging system. If humanity or its descendants still exist, they will witness the birth of stars on a scale never before seen from within our own galaxy. They will see the sky filled not just with ancient stars, but with new ones, young and bright, their light a testament to the creative power of the merger. The collision will not end our story. It will add new chapters, new possibilities, new stars under which future beings might live and wonder. After the merger is complete, perhaps 5 or 6 billion years from now, the Milky Way and Andromeda will no longer exist as separate entities. In their place will be a large elliptical galaxy, sometimes nicknamed Milkomeda in popular discussions. Our Sun, if it still exists, will orbit within this new galaxy on a path determined by the chaotic gravitational interactions during the merger. The night sky will look completely different. Instead of the band of the Milky Way stretching across the heavens, observers will see a smooth glow of stars in all directions, the characteristic appearance from within an elliptical galaxy. The familiar constellations will be long gone, scattered by the gravitational reshuffling. It will be a new cosmic era for any life that witnesses it. The merger of our galaxy with Andromeda connects us personally to the cosmic processes we have explored tonight. It is a reminder that we are not separate from the universe but part of it. Our galaxy is participating in the same evolutionary processes that have shaped cosmic structure throughout the age of the universe. In 4 billion years, our cosmic address will change, but the atoms that make up our world, the carbon in our bodies, the oxygen we breathe, will persist, incorporated into the new galaxy. We are made of star stuff, as Carl Sagan said, and we are embedded in galactic stuff as well. The story of galactic cannibalism is not just a story about distant objects. It is, ultimately, our story too. We have journeyed far together, from the first gravitational whispers between distant galaxies to the final merger creating something new. We have witnessed the formation of tidal streams, the collision of supermassive black holes, the ignition of starbursts, and the transformation of spirals into ellipticals. We have learned that galactic cannibalism is not destruction, but transformation, not an ending, but a continuation of cosmic evolution in new forms. Now, as we prepare to conclude our journey, let us take one final step back and consider what all of this means from the broadest possible perspective. What do these processes tell us about the nature of the universe itself? The universe is fundamentally dynamic. Yeah, nothing is truly static. Everything changes, evolves, transforms. Galaxies merge. Stars are born and die. Elements are forged and dispersed. Even space itself is expanding, carrying distant galaxies away from us at ever-increasing speeds. Change is not a deviation from the cosmic norm. It is the norm. The universe is a system perpetually in flux, driven by physical laws that ensure continuous transformation across all scales, from the quantum to the cosmological. Galactic cannibalism is just one manifestation of this deeper truth. It is the universe's way of ensuring that structure never becomes stagnant, that complexity continues to increase, that the cosmos remains forever interesting and unpredictable. There is a deep pattern here that appears at many levels. Individual stars form from clouds of gas, live their lives, and return their enriched material to space when they die. That material forms new stars, creating a cycle of stellar birth and death. Galaxies follow a similar pattern on a grander scale. They form from primordial gas, grow through accretion and merger, and redistribute their matter through tidal streams and eventual dissolution or transformation. Even the universe as a whole emerged from the Big Bang, evolved through various epochs, and will continue evolving into the far future. At every scale, we see the same principle at work. Matter and energy are conserved, but they are continuously reorganized into new patterns and structures. This is cosmic recycling in its purest form. Galactic cannibalism also reveals something profound about the nature of violence and creation in the universe. We use words like collision, destruction, and cannibalism, which carry negative connotations in human experience. But the universe is not bound by human values. What appears violent to us is simply transformation to the cosmos. The energy released in a galactic merger, the disruption of structures, the scattering of stars, these are not moral events. They are physical events, governed by impersonal laws without intent or malice. And remarkably, these apparently violent processes are the very mechanisms that create complexity, forge new elements, birth new stars, and drive cosmic evolution forward. Creation and destruction are not opposites in the cosmos. They are two aspects of the same process. From a human perspective, the timescales involved in galactic cannibalism are almost incomprehensible. Billions of years from first approach to final merger. We measure our lives in decades, our civilizations in centuries or millennia. The idea of a process unfolding over billions of years is beyond our intuitive grasp. Yet this is the tempo of cosmic change. The universe is patient. It works on timescales that dwarf human history, that dwarf even the existence of life on Earth. This perspective can be humbling, reminding us of our small place in the cosmic order. But it can also be liberating, showing us that the universe operates on principles that transcend our immediate concerns, and that there is a grandeur to existence that extends far beyond our brief moment in time. Despite the impersonal nature of cosmic processes, there is undeniable beauty in what we have explored. The graceful arcs of tidal tails, the brilliant glow of starburst regions, the majestic transformation of spirals into ellipticals. The universe creates art on the grandest scale imaginable, and it does so without conscious intent, purely through the operation of physical law. This suggests something profound. Beauty is not merely in the eye of the beholder. It is woven into the fabric of reality itself. The mathematics that governs galactic interactions produces aesthetically pleasing results. The same equations that describe orbits and gravity also describe elegant, flowing structures visible across millions of light years. Science and art converge in the cosmos, revealing that truth and beauty may be two aspects of the same underlying reality. As we conclude our journey through galactic cannibalism, I want to leave you with one final thought. The story we have explored tonight is ongoing. It is happening right now in countless locations across the universe. Galaxies are approaching each other. Tidal streams are forming. Black holes are merging. New stars are being born. And this process will continue for billions of years into the future, long after humanity has come and gone, long after our sun has burned out, perhaps long after the last stars in our galaxy have faded. The cosmic dance continues, indifferent to observers yet magnificent to behold. We have been privileged to witness a small part of it, to understand it through science, and to appreciate its profound beauty. Thank you for journeying with me through the serene and eternal process of galactic transformation. Our cosmic journey through galactic cannibalism has come to an end, but the universe's story continues forever. The next time you look up at the night sky, remember that you are seeing not a static backdrop, but a dynamic, evolving cosmos. Those distant points of light are galaxies dancing together across billions of years, stars being born and dying, matter being recycled into ever more complex forms. You are made of atoms forged in stellar furnaces and dispersed through processes like the ones we explored tonight. You are part of this grand cosmic story, connected to everything from the smallest particle to the largest galactic supercluster. If this journey has brought you a sense of peace, perspective, or wonder, consider subscribing to Cosmic Calm for more explorations of our magnificent universe. Until we meet again, may you rest well under the eternal stars.